Let's continue. So let's first try to solve this. How we can solve this? We take the Fourier transform. We solve it with help of Fourier transform. I remind that we have operator minus ddx, and you can write this equation as d squared plus identity f equals to delta of x. Then take Fourier transform. Do you remember the commutation property of Fourier and operator d? It is m squared plus identity yes. So it is y squared plus 1 f hat and so you obtain your solution with the help of inverse Fourier transform. Yes? And on previous seminar we calculated, but we calculated the direct Fourier. Here we have inverse Fourier. It depends only by the sign, but we can repeat it. We know that I take with contour integral. So we have one pole I in up contour, and have if we take this contour, we have minus I. But when we have, we need that this exponent vanishes on this semicircle. Yes, because we must obtain the integral only on real axis. So our function must decrease on the up half circle. So if I take y. So if we have y with positive imaginary part, so I. So it gives us exponent minus x. It works for positive axis, it works for negative axis. For positive and negative x, this function exponentially go to 0 on this contour, on this part of the contour, on the half of circle. So we have it as 1, 2 pi, 2 pi. Should I remember something on residuals or not? It is known fact, yes? Okay. In this. And minus here additional minus because we have the negative orientation of contour, and another sign of pole. This, but 2 minus, so we can write it as what happens. This reduced from this, I reduced from this I, and we can write the common answer. So the solution of this equation is, and it is, yes, it is green function form. So if you write this equation with some right part, G, then the partial solution will be the convolution. So some knowledge for convolutions. Let's discuss it. Definition. We have two functions. We want to define the convolution at point x. The definition is the integral this is convolution of two functions. For what functions you can easily define or prove the existence of convolutions? For distribution, no. What it means for distribution, for example? Yeah, later we define for distributions, but not for any distribution. L2, yes, but the result is not good. Yes, it exists because you can consider it a scalar product with some changing variables, yes? Yes, for function from L2, the convolution exists, and it is function from C0. So theorem following, f g belongs to L2, then they exist f convoluted with g, but it is in C. It is not a theorem, it is exercise. It is just like an exercise. But theorem following, and we'll just prove it. So it is algebra. L1 capital is algebra. When multiplication is a convolution. The sum of functions from L1, it is a linear space, the sum of functions is function from L1, but usual multiplication is not from L1. But if we take convolution as multiplication, we L1 change to the algebra. Yes, yes, we just prove it. But association is very easy because it's Fubini theorem. It's just the Fubini theorem, yes, changing variables. Why this? Is it obvious? Yes? But then the integral it is obvious too. And change variables. So here, for example, was u, v, for any fixed v, you integrate by this parallel set of axes, yes, of lines. But here you can change variables and you integrate it on this. You integrate in one direction, so in another direction it is in L1. So from this we conclude that ft g x minus t dt belongs to L1. Property. Properties of convolutions. Property of convolution. Is it clear or not? It's changing of variables, just nothing. This is clear property. It's linearity of integral. It is linearity of integral. But you can consider a convolution as a linear operator. Here, all functions f, g, h belongs to L1. So what you can take, f fixed, define operator as capital sub f, a convolution with function f. It is linear operator. It is linear operator. Moreover, it is easy to see that this is it is bounded operator. It is bounded operator.
Why it is not equal?
Why it is, you can prove that it is equal. Of course, you can prove that it is equal. But when you take absolute values of integral inside, you can take inequality, yes?
Oh, yeah.
But then you can show that it is equal, of course. Third, properties in L1. Because few minutes later, we defined convolution for distributions. This property is not valid for distributions. It is not associative.
No.
But for an L1, it is associative because it's Fubini theorem. It's just Fubini theorem. You prove it with Fubini theorem. For f L1 and have derivative, and derivative is 2L1. Then the convolution is differentiable. It can be calculated as following. What you can say about the support of convolution? The support of convolution lies in the sum of supports. What it means sum? Sum means in a theoretical sense, so x from here equals to t1 plus t2. From this. Why? Because convolution at point x equals ft gx minus t. You can see that this x equals t plus x minus t. Just arguments of this function. And if some point's not in support, so it is 0, yes? If some arguments is not in support of corresponding function, then one of this factor is 0. Then it is 0. So, see. And the important property of convolution it is a product of up to the constant. Up to the constant, in our situation, it will be, in our definition, and multiplicative is a more easy operation than integration. But Fourier transform is integration, but humanity have a lot of tables of Fourier transform. Why it is so? Yes? It's just, this is convolution, and this is Fourier transform of this convolution. Then Fubini. This Fubini theorem. You can do it because functions are integrable. And in the interior integral, change the variables. Change the variables. X minus t equals to s. So this integral changed to what integral? G of s exponent yes? And you see that our integral changed to the product of two integrals. It changed to the product of two integrals. Here I lost y. You have two Fourier transform, but only one this factor. So it is equal to question about what, Hasis? Here, from here, this integral to this integral, I go with the help of Fubini theorem. And for interior integral, I change the variables. X minus c is s. So gs exponent t plus s on y, dx is equal to ds. And you see that the variables lives apart in the different integrals. Ft, I take this exponent, exponent ity for this, and isy go to gs. So we have two Fourier transforms, but only one this factor. So it is equal to this. Okay? And now let's. You ask why this? Because we define the Fourier transform with this factor before integral. But we have only one. We have two integrals, but only one factor. So I divide on this and multiplicate on this to obtain two Fourier transforms. I write Fourier transform with this factor. And now let's try to define the convolution of test function and distribution. So let belong to L1. I take regular situation. Then That's all. So we define. Now you can define for all. We take the definition. What is the result of convolution of test function and distribution? The action of functionals is a constant, yes? But we have a change of variables which depends on x. So we obtain the constant depends on x. It is a function. So convolution of test function and distribution is the usual function. Moreover, it is smooth function. It is smooth function. What is the convolution with delta function? What is convolution with delta function? By definition, what gives us delta functions? It's evaluate the values at 0, yes? So we must put except t 0. So convolution with delta function is identity operator. You can write it as delta, as we write, is identity operator. Yes, and for example, what is convolution with derivative of delta function? What is convolution with derivative of delta function? Again, use the definition. Use the definition. It is delta prime t phi x minus t. Then by definition it is minus delta of t phi. Oh, you put derivative on phi, yes? But derivative by t, and here we have minus. So minus phi so convolution with delta is derivative. With delta prime is derivative. So you can write that as delta equals d or dx. And now you can obtain why we use this. So if you have some differential operator, L f equals sum a k phi k, k. Let's for simplicity with constant coefficients. And you must you want to find the partial solution. Of course, the general solution looks like the solution of homogeneous equation plus some partial. Yes. How we can find this? You write a new equation with delta function, and you solve it in distributions because we have delta functions. The solution is fundamental solution. Usually it denotes as E capital of x. Then partial solution equals to convolution of this. Why? Why it is solution? Because LF partial equals LEX. We know that convolution is linear. It is equals, by definition of fundamental solution, delta function. And we know that convolution with delta is identity operator. So it is a real solution. It is a real solution. Yes, we'll look for the simple example, yes? And now convolution of
But the question is, can you find all solutions for this?
all solution looks like the solutions of homogeneous equation plus some partial. Homogeneous with, for example, for simple constant, you write the characteristic polynomial, find its kernels, roots, and write the general solution of homogeneous equation. For constant coefficients, it's no problem. If coefficients are functions, it is another problem. It is another problem.
The fundamental solution is not unique. Fundamental solution.
Maybe because partial may be another, for example. You can change here and you obtain some another fundamental solution. But with Fourier transform, we find the unique solution with delta function in our example.
With the same delta Dirac, we can have another fundamental solution. With the same delta Dirac, if we put delta Dirac and try to find the fundamental solution.
You can change. You want to change this?
No, with this fix, there is only one fundamental solution.
Yes.
Because in physics, with this delta, we have different fundamental solutions.
Yes, of course, up to polynomial.
Okay.
The kernel of a kernel of homogeneous equation. Yes. It is not unique, because you can add to any function from the kernel of operator. Of kernel of operator, yes. Convolutions of distributions. It is a question, can we obtain this? In general situation, answer no. In general situation, answer is no. But in some situation, it is possible. First, I want to emphasize that the D is dense in D prime in dual space in star weak topology. So it is main idea to obtain new operations on distributions. You have a good operator on test function. Test functions are dense. So you can try to find the continuation of this operation on distribution. So let this function with finite support. It is important. So I want to obtain that the convolution of distributions is a distribution. How we can do it? If they are indeed they are regular distributions, so the action is an integral. This is convolution, this is action of operator. Then, of course, this from D, the finite support, Fubini theorem valid, yes? Use Fubini theorem, you can write it as f of t. Here you use the change of variables, x minus t equals to s. Then x equals to t plus s, dx equals ds. You can write it as following. Here I need to write arguments. Yes? And you can take it as a definition, but it is not correct definition. What can be problem? Here you see, here we write the action of distribution on test function. It depends on parameter t. We write the integral in parameter s, but it depends on parameter t. It is some function psi of t. What can be problem with this function? What can be problem for this function?
Not be attached to.
Yes, it can be. It is smooth, of course. It is smooth, but it can be not find its support. So this function maybe is not from D. So we can't take it as a definition. But sometimes can. When it will be with compact support? When the result of this will be compact support. For example, if function phi from D, yes, it has compact support. And we know the situation with property of convolutions. The support of convolution lies in sum of supports. So if support of G of S is compact 2, so it's function from E prime, distribution with compact supports, then this will be compact support. And this is from compact. So you can define the convolutions, for example, for distributions with compact support. But it is very strictly assumption. Because you can see what happens here, for example, or here in convolution. In convolution, we integrate by x, yes? Imagine that the support of each function lies on semi-axis. On semi-axis to this, for example. What happens here? You change the support, yes, and take it in another orientation, another sign. So intersection of supports is compact. So I defined function. So space D plus, it is D. It is consists of function phi from D, such that support of phi is compact, but lies on this. And then you can define D prime plus. D prime plus, it is functionals from F D prime with support lies here. Then the convolution, they exist F G, and it lies in D plus. And the definition we take the F G acting on F, definition F of T, G of S, phi T plus S. That's a definition. Who can calculate this convolution? Let's take brackets as following. Convolution with delta prime is derivative. Yes? So it is 0. Theta equals to 0. Now put brackets in this order. Again, convolution with delta prime is derivative. The derivative distributional sense of theta function is delta function. Convolution with delta function is identity operator. Not associative. Why? What is the problem? In what function is the problem? The problem only in one function. One. It is not from support is not bounded. Theorem on D plus is associative. On this set, the convolution is associative. And what we can do with this space and with convolution? I remind the old our problem. We have operator of integration. How looks like its powers? How looks like its powers? Is it very similar to convolution? Ft x minus t. It is like convolution, but we have integral not on all x's. We have only integral from 0 to x. If function f from d plus, then the integral equals to 0, yes? Because support for negative semi-axis function is 0. So for function for this class, the integral will start from 0. But what we can do if we want to obtain here x? There is standard class of functions in distributions. In distributions, for example, there with subindex plus. In distribution, it means only this. And similarly, you can define functions with symbol minus. So what is the equality for this function? X minus t. It is x minus t alpha as x minus t positive and x minus t alpha if, and 0 fx minus t negative. It means t larger than x. So integral exists only if t less than x. It is not non-zero if t less than x. So you can write it as convolution with function x n minus 1 plus n minus 1 factorial function f. Moreover, this function belongs to the d prime plus. But here we have integer parameter n. And here I can write arbitrary parameter, maybe complex. Can you define so the primitive or derivative of the fractional order with help of these integrals, with convolutions, with some distributions? Yes, you can. For example, take alpha from 0 to 1. Consider function psi alpha how change n minus 1 factorial? I consider gamma functions. I use that gamma of n equals n minus 1 factorial. And then you can define the integration of order alpha on f. It is convolution of this function with f. So if alpha is positive, it is primitive of fractional order. If alpha is negative, we define as derivative of fractional order. Let's consider example. Can we find the derivative of half order of theta function? What is the one? We show that in distributions always exist primitive. We show it. And it is unique up to the constant additive. So what is the primitive of theta function? X plus. This function looks like here 0, here x. Is distributional derivative, here 0, here 1, is theta function. It's just theta function. So it is one of derivative. But what is the half of derivative? What is the half of derivative? Let's, by definition. I write the convolution with this function. What is the gamma of 1/2? What is the value of gamma function in 1/2? Who remember? Square. Any correct formula must contain square root of 2, pi, and e. Yes? Square root of pi, yeah. Yes? Is it correct answer or not? I need to write additional one symbol for correctness of answer. In what space we work? On what we define it? These convolutions for distributions. In space. So we need to write here plus. Square root of x exists for positive x. So it must lie on positive sub-axis. We have a strange factor, but it's easy to see. This is operator has a group property. So it have a group property on space, on this space. So it is easy to check that it is just integration. It is just a primitive with the help of beta functions. Here, beta functions arised, which you can calculate with gamma function, for example. Some tasks. Okay. First, how we can calculate this convolution? It's just in L1. Not difficult. It is in L1, in L2. Yes? First function characteristic gives us an integral from 1 to 2, and here we have integrate this function. So it is 1 equals to 1 if x minus t, yes? So it is equals to 1 if t So you see the distance between these bounds are 1, yes? And here integration is 1. So situation is following. You integrate by interval 1, 2, but here we have a characteristic function for this, yes? You can rewrite it as characteristic function of the interval x minus 4, x minus 3, but of t. So let's start from the very small x. If x very small, this support lies here. The supports not intersect, the result is 0. Then you move this support to the right, yes? What situation happens when we start to obtain not 0? We start to obtain not 0 when x minus 3 here, x minus 4 here, yes? So x minus 3, and then it is x from 5 to 4, and we obtain the integral from 1 to x minus 3 dt, it is x minus 4. Yes? Then x minus 3 go out, integration, and you x minus 4 to x minus 3. So if x minus 4 here, x from 5 to 6, we obtain the result x minus 4 to 2 dt equals, as picture you can see it is and you can check the property of supports. What is the sum of supports? This smallest sum 1 plus 3, 4. Largest 4 to 6. Support lies on the interval from 4 to 6. And you can see really that it is lies in this interval. And you obtain but convolution not only L1, it is a continuous function. It is continuous function. Who can calculate the Fourier transform of theta function? First, I propose to calculate of this function, Fourier transform. How we can calculate it? It is limit of this function. And for if epsilon is not 0, this function is very good function. It is from L2. Yes? Not from L1, but from L2. The Fourier transform of functions from L2 is function from L2. We know its property. It's unitary operator. So let's calculate, find the Fourier transform in L2 of this function, and then take this limit. We need only pointwise limit as integral. In star weak sense, it exists in distributions. So what you can say about this integral? Again, we calculated with the contour integration with residuals, with the help of residuals. What we can say about this integral? We take the upper half circle for y is negative for Fourier transform, direct Fourier transform, and the lower if y is positive. But our residual is minus I epsilon. Here no residuals, yes? And here we have residual minus I epsilon. So this is integral equals 0 if y less than 1 is negative. Because we have no singularity of function here. But for this, we have residual, and we have negative orientation, yes? So it equals minus E minus epsilon y divided on 1. And now take the limit. Take the limit. To what it tends f epsilon goes to 0. So it equals to minus theta. So Fourier transform of so you can just now, can you obtain the Fourier transform of theta function, Heaviside theta function? What we know about property of Fourier transform in spaces when we have the inverse formula? What gives it? F minus x. In all space when we have this property. We have this property in S, in L2, and in S prime. So minus theta y equals I change the signs, minus here, multiplicated, I obtain this result. Okay, another problem. When we start convolutions, you want to find the convolutions from the space L2. So, third problems prove that if G equals to L2, R, then you can see this on this convolution. It depends on x, but you can consider it as scalar product ft g x minus t. Yes? We consider this convolution as a scalar product of these two functions. What we know about Fourier transform in L2? It is unitary operator. It preserves scalar product. So we can write that it is so you need to calculate this. In parameter t. Again, changing of variables, x minus t equals to s, t equals x minus s, dt equals minus ds. So you obtain integral infinity minus infinity g of s e x minus sy minus ds. Then you change the order of integration and take away this minus. So you obtain minus infinity infinity g of s e minus sy ds, and here you obtain e minus xy. So it is multiplication. So it is equal, we obtain that this Fourier transform equals, so g x minus t Fourier transform equals to this. Yes? Then you can write it as following. It is scalar product then again write the scalar product as integral. What you can say about this function? Multiplication of functions from L2. Two functions from L2. It is function from L1.
Oh.
Because it's scalar product. It's function from L1. And here is written is Fourier transform for function from L1. Exponent Fourier transform for function from L1. Fourier transform for function from L1 belongs to what space? C0. So I automatically obtain that it is from C0. And one more thing, I have time. Convolutions in L2 with distribution. We can define for some distributions, we can define the convolution with function from L2. So f is from C prime such that how we can define this? And what is the spectrum of this operator? I want to define this convolution as operator defined by this function. We fix this function and changing function g from L2. We obtain some convolution is linear operation. We obtain some linear operator. Why I want this? I want this to obtain the bounded operator. What I know? I know that Fourier transform change function from L2 to what functions? I know that Fourier transform walks from L2 to L2, and Fourier transform walks from S prime to S prime. We have here operator of convolution with some function. Here walks Fourier transform. We again get in L2 what operators appears here. And I want that the diagram will be commutative. I want the diagram will be commutative. Here appears some operator B. Commutative diagram means what? Means S F then Fourier transform must be Fourier transform then B. But what do the Fourier transform for good functions? It is product. It is product, yes? So it is this. So operator of convolution is similar to what operator? Multiplication on this function. So if Fourier transform is bounded, then your operator is bounded. You can easily find the spectrum of this operator. Yes, it is the values of this function. So operator of convolution is similar to operator B, where B is written here. B H is multiplication on Fourier transform of F on function H. H from L2. I change G hat on H. So operator of convolution with function with distribution. But what you need only that Fourier transform of distribution will be good function. Will be a good function, bounded function. Example. In quantum mechanics, so appears operator, Hilbert operator. One over pi and principal value of this integral, the Hilbert operator. Find the spectrum of this operator. Can you find the spectrum of this operator? It is a convolution. With what distribution? With what distribution? I write it today. This distribution. Yeah. 1 over pi. So we need to find this. How calculate this Fourier transform of P1 of x? How we can find it? There is a Sukhotski identity. We calculate the Fourier transform of this function, yes? So, who do safe change calculations? What is the result? Daniel, can you say me?
Minus theta
minus theta on square root, yeah? It's not correct. I forget something when calculate this. I know what I forget. The contour integral equal to what? Contour integral. When 2 pi e and sum of residuals. I forget this factor. I forget this factor. Change. Check this. I forget this. So answer must be equals 2 pi I multiplied on this minus theta this. Yes? If we take this factor. Then the result equals minus e theta 2 pi. Oh, not here. This. What you can take out? It is square root of p over 2, like this. And 1/2 minus theta equals to what? Here 1/2, here minus 1/2. What is that function? Minus signum y divided on 2. Yes? So we obtain that equals to what? To this. So what is the spectrum of Hilbert operator? Hilbert operator is similar to what operator? So operator A is similar to operator B, where BH square root 2 of P multiplied minus I square root of P of signum on H. And we have additional 1 over P. Yes, this factor. 1 over P special. So 1 over P here. So what we see? Minus signum YH. Yes? I. So the spectrum of this operator plus minus I. And it is point spectrum. It is point spectrum. Because function is constant. Function is constant, moreover it is eigenvalues of infinite multiplicity. Somewhat about pseudo-differential operators. 2 words. 5 minutes on pseudo-differential operators. Let's consider L, F, Alpha is multi-index. Is a multi-index. И d alpha equals d alpha 1 x1, d alpha 2 x2, d alpha n xn. Partial derivatives, maybe. Partial derivatives. Here operator d will be something another. It will be, we consider operator d, this operator, e dx, yes, in one-dimensional situation. But just now we consider d1x is minus e dx. Because why minus here? Do you remember the commutational corresponding between Fourier transform multiplication on variable and this and derivatives? For this we have fd minus f, but for this minus we have f dx m Fourier transform. So it's just a multiplication on a variable. Yes, it is multiplication of variable. So it is xi this one variable. And let's consider this operator from, for example, function f from S. Imagine that function f from S, from good space. You know that in this situation, we have property that this is identity operator. Let's write this operator in this form. Now this in this form. No, what I want. Yeah. This. Then you can commutate Fourier transform with this. Yes? You can commutate this operator with this. You obtain this.
But why you take out the factor function, the function a?
Xi alpha equals xi1 alpha 1, xn alpha n. It is multi-index, multi-variable. We have an n-dimensional situation for each variable. For each variable. So you can write it in the form integral 1 over 2p n with inverse and it is scalar product for n-dimensional vectors. For inverse, it is integral for Rn, alpha x, xi alpha, f d xi, and I forget some for alpha. Here the sum for alpha from 0 to m. And this is, the notation is alpha 1 plus alpha n. Immediately we start with the multidimensional Fourier transform. We study one-dimensional. Here we use this approach for multidimensional. This is named the symbol of pseudo-differential operator. We start with a usual operator. It is usual differential operator, yes? And here we write it in integral form with some symbol. Here, I rewrite it. LF equals 1 to Pn integral E x xi sum alpha a alpha x xi alpha f dxi. This is equals px xi. This is symbol of pseudo-differential operator. What you can say about this symbol from the point of view of variable xi? What is the function? A alpha good function, smooth function, for simplicity. What you say about this function, this symbol, as a function from xi? For xi. What is the function of xi? Polynomial, yes. For usual differential operator, this function is polynomial. But now you can define pseudo-differential operator when you change the symbol. You can consider function of any dependence of xi. Any dependence on xi, but with growth not larger than polynomial. So you can define this p of x xi, not polynomial, but constant c1 plus xi m. Exists constant c, exists power m, that it grows not larger than polynomial. And you consider the integral operator with such symbol. And you name this operator with such symbol a pseudo-differential operator. One example. Let's consider Laplacian operator. What is the symbol of Laplacian operator? All functions are constants. Moreover, all functions A alpha equals to 1. Yes? This is d squared. So the symbol but for example, you can consider not polynomials, but you can consider fractional powers. You can consider fractional powers, you construct analogous of fractional derivatives. You can consider any function from xi, good, smooth function from xi, but not polynomials. And you obtain a class of operator, integral operator, which are named pseudo-differential operator. Because if it is polynomial, it is just a usual differential operator. Okay, is it clear? So that's all.